In this video, we're going to be learning how to apply a lot of probability concepts we have learned in the lecture in a very common type of problem through a contingency table. So let's look over to my screen on the computer here, and a table like this is called a contingency table. And commonly, people also refer to this as a two-way table. It got rows indicating the kind of values in one categories, and it has columns indicating different types of data in the different categories. And then surprisingly, a table like this, we can answer a lot of probability questions. So let me now, back to my writing board here, let me now call that example 5 to continue with our example we've done through the lecture. So here's example 5. And so let's look back at our table here one more time. And this table described a classroom at a university where we have 104 students total. And in that classroom, we have these four majors here. We have some students are being business majors, some students in that class is being a math major, some students are being an engineering major, and some students being in science major. So some kind of course there's whatever that is, having these different majors being found in that class. And furthermore, we're looking at different class ranks here. There are freshmen, there are sophomores, there are juniors, and there are seniors. And that's all made up a total of 104 students. And so, due to the nature of two ways table, then any of these values here in a cell entry is contingent upon the other values on the other cells. And that is the reason why a lot of time two ways tables are also referred to as a contingency table. And so, but we're not aiming at explaining too much about what a contingency table is, but now let's see how we can answer a lot of probability questions out of a contingency table like this. Okay, and so throughout this entire example, to reach as many problems as we can do, then this time start allowing me to write all of the question in symbolic statements here. So, question A of the example. Let's go from the easier level and start rising up the level of difficulty. So here, question A, I'm looking at P in parentheses. So find the probability of being a about junior. And so at this point, if we recall from our lecture that P in parentheses means find the probability, and then the event here we're looking at, think about if we go into that classroom and randomly select one student, then the chance of finding a junior is going to be. And so now, to get an explanation of this, let's get back on my board here. But all the class rank, as I have briefly explained earlier, then all class ranks are being arranged throughout the rows right here. So we just easily look for the junior row, the entire row of junior here. But we got one business, we got 2 math major, we got 10 engineering. So the entire row here, and where it hits to the row total right there, now gives me 14 junior students, and being out of the whole sample space 104, which in turn reduces down to 7 out of 52. And that's how I find the answer to my first question. In question B, how about let's find the parentheses for having an engineer major in that class. And so this time the different majors are being arranged in the columns, and so in that way my engineer column is right here, which total up into a column total down here being 70. And so that concludes my probability that finding an engineering major in this class. The probability for that is 70 out of 104, and which in turn reduces down to 35 out of 52. In a different question, how about question C? Find the probability of selecting a sophomore and being in science major. So once again, back into the table. As a reminder, the way how this table presents data to us, then classes or class ranks are being arranged in a rows right here, which ends up into these row totals. And on the other hand, the majors are being arranged into the vertical columns here. And so now we're looking for that compound event being sophomore and at the same time being in a science major. And I spent a lot of time explaining how to understand the compound event A and B. And so in a contingency table like this, usually a successful strategy for getting this kind of problem work is to shade the column and the rows that meet the two requirements. So being in science, as in this column, I am going to shade that column. In this case, we actually don't need to run all the way down to the column total. But so I'm going to choose that color, the light purple here, to shade my science column. So this indicates those outcomes that meet the events being in the science major. And then being sophomore, now I'm going to locate for that row right here, and I am going to highlight that row in a light pinkish right here. But now as we highlight through the row right there, then we're going to start noticing some intersection or overlapping of the two colors. And this is where this entry right here, or these outcomes being in this entry, are indicating those outcomes that meet the two requirements simultaneously. So being science and being sophomore is right in here. And so now we are ready to conclude our final probability. So the probability of finding a sophomore and science major in this class is, the table now is saying 2 out of the entire sample space, 104. And once again, which in turn reduces down to 1 out of 52. And now when it comes to another question, question D here of the example 5, let's find the probability of, how about being in math major or being in the junior class. And so I explained through the lecture that anytime approaching this probability problem where it has the compound events with the OR logical keyword, then we have two approaches. However, when we are going in a contingency table like this, then I highly recommend to use the additional rule as that formula, because through counting is going to actually make it more, solving the problem here through counting, that's what I meant, is going to make it more, a lot more challenging actually. And so the additional rule now is stating that we can just simply, and experience in telling me that anytime I'm looking at the compound events with the OR logical keyword here, then I'm always going to treat this OR here as a separator. Why is it a separator? Because we can separate the problem into two separate probabilities. So now I'm going to find one separate probability for math. I am going to find one separate probability for junior. And the two separate probability, I am going to add them up. And then we are going to subtract the probability of being math and junior. And therefore, in that way, now tearing it down into and laying down the additional rules right here, then we can easily find each one of these probability using the method that we have seen back in question A and B previously. And so, once again, allow me to highlight my rows in my column, but math major is in this column right here, where it hits all the way down to a row total, to a column total. I meant column total being 18 out of 104. And then on the other hand, the junior class is located in this row, which highlighted through a light purple color right here, and it runs all the way to a row, to the row total right there being a 14. So we can easily find that the probability of being a junior in this class is 14 out of 104. And then don't forget, the formula says we need to subtract out the probability of those who are at the same time being in math major and being in junior. So one more time, looking back at the table, we can conveniently see that highlighting the column and highlighting the row, creating naturally that row and column intersection right here, and it's clearly nailed down for us which entry is indicating the outcomes that meet two requirements. So right here we're looking at two outcomes that meet both requirements. So that means we are subtracting out 2 out of 104. And so now I purposely left these fractions irreduced so that it's easier to do the calculation at this final step here. But so now the math turns out being 30 out of 104, which reduces down to 15 out of 52. And that's how we're done with this question right here. And now let's introduce some negations to our probability questions. And so let's now look at question F in the same example. So let's look at probability of, I'm going to pick some primary events first. About being junior and the other primary event I'm going to be looking at math. But now unfortunately I am going to put a negation here. Alright, and so before we get started, I must explain about how negation work in symbolic statements like this. But you see, this negation here being put right in front of junior. So in the way how it's written, then it's intended, or it's only meant to be negating this event only. Or in other words, in the way how this looks right here, this negation only attached to whichever the events that immediately right after that. And so in how I am explaining, then math is actually not being negated. We are only negating junior. Math, we are looking for math. So in that way, so now looking at our table, being not junior means we are anywhere outside of this junior row. So allow me to start putting up the highlights. So these are the highlights that's indicating we're outside of the junior row, because remember, we want non-junior. And then this highlighted column in the light purple color is actually indicating we are looking for math. And so in that way, and remember I explained already that the negation we saw in this statement is only negating junior. So math, we're leaving it the same, not negated. And so in that way, there's my only one column being highlighted for math. And so anywhere my column for math here intersecting with the pink, that's where those are the entry that goes into our count like that. And so these entries will answer the probability of being not junior and at the same time being a math major. And so back to our problem here, then the way to write out the answer, we just simply now going to total up all those counts that we saw intersecting between the two colors. So there's 10, and there's another 5, and there's another 1 in that purple, light purple column, and all of that is over 104, which in turn give me a total of 16 over 104, and that reduces down to 2 out of 13. And so let's get off track here a little bit. But what we've learned now, what we've seen as an experience just now from that question F there that we've done in example 5, then let's say you have a compound event A and B here. And then let's now put up a scenario where we can have a negation here in the way how it looked, or another way that we can put a negation there with that B in behind the AND keyword, or some compound statements symbolically has both negations attached to each of these. And so allow me to explain this in the assumption that you haven't done any formal course or any formal training in logic. And so I have to explain it this way, that not convincing to some people, but I have, like I said again, I have to assume that not all of you, or I actually have to assume that you haven't done any formal logic course here, because sadly the logic is not required as part of our class at all. But so when you had these three main structure right here, then remember what I explained earlier is the negation only associated or only attached with that event immediately following it. And so in this first form right here, then this negation is only attaching to A. That means A is being negated by that not, but this B right here is not negated, so B here has nothing to do with that negation from the very beginning. And then so similarly in that same argument right there, then this negation in my next form right down here is only negating B. It has nothing to do with A, meaning A is the same way it is, not negated, but B is being negated. And then in the other case here where you see two negations, then we have this negation is attached to A and this other negation is attached to B here. And like I said, some viewers who are watching this video of mine right here, and you know some other ways of logically re-expressing this statement right here, that's a good plus for you. But I'm assuming that if you know that way, then you already have done some logic course or at least some basic background. But this video is aimed at the students who haven't done any logic at all. And so the same thing, the similar thing can happen to the other kind of compound event, A or B. You can have two primary events being connected in a compound statement with the OR logical keyword between, and sometimes there's only one negation word that happens right before the A. No fancy parentheses or anything like that. And then it could be, again, we have a compound event with the logical keyword OR connecting between the two primary events, but we have a negation that attached, that stays with the B right here, or there's another time that we have the two primary events and they both come with the negations. And so once again, assuming that you haven't done any logic course, then I can quickly explain that this negation here, in a way exactly how it looks right here, then that negation is only attached to that event, whichever the events that immediately following it. And so meaning in the way how it looks right there, symbolically, this event B right here won't be negated. It stays the same way it is. And then so in that in that way of arguing it, then this negation in my next form right here, the negation here I'm indicating with the red arrow is only attaching to B, and A is not negated. And then when it comes down to this last form right here, then this negation is for A and this other negation is for B. And this negation has nothing to do with B, and this negation has nothing to do with A. And so those are, you can rewind the video a little bit to learn about again the other forms, and you can pause the video to take careful notes on these. But that's going to be our sort of like our guidelines for the rest of these other questions. Symbolically, anytime that there's a negation that comes in and being scattered here and there in your probability questions. All right, so taking from what we learned, then let's do another question back in this example. So let's say find the probability where we're looking at not sophomore and not engineer. Or how about I've done engineer for too often, so how about not math? All right. And so once again, this negation is only attached to sophomore. So sophomore is being negated by that negation symbol right here. But this negation has nothing to do with math. Math is being negated by this not. And so the chart I brought up earlier to explain now means we're treating not math as one event and being not sophomore as another event. And that's what the whole idea about being attached to is all about, being grouped to is all about. And so now taking that understanding, not sophomore is one event and not math is another event. So here we're still in the end looking for the outcome that meets the two requirements here together, the intersection of not sophomore and not math. And so back into my chart again, back into my contingency table. The non-sophomores are in these rows, and the non-math major are in the columns with the light pink color ran through it. And so now, once again, the overlapping of the two colors would be where we identify those outcomes. And so in that way, those outcomes that meet the two requirements, non-sophomore and non-math major, let's now go ahead and look through the table one more time and collect all of the intersection entries right here. We got 5 in column 1, plus 1, and we have 35 here in column 3, plus 10 plus 5, and we have another 3 in column 4, plus 1, and all of these different entries right here being totaled up and divided by 100.04. And like I said again, I'm not saying that I'm explaining this way of doing it in the fastest way, but it's in a way that assuming my students who are viewing this have not done any courses in logic at all. And so the math now gives me 62 out of 104, which reduces down to 31 over 52. Let's now see part H of the example. About find the probability of not business or being in junior class. All right. And so, once again, taking that explanation you've seen earlier and previously, and which has been applied in 2 problems already. And so, this negation not right here is only grouped together or only attached together with business right here. And so, that here is one event, and the other one, junior, here is being one event on its own right here, not being negated. And so, in that way, let's look at our table, our contingency table right here. So the non-business would be these highlighted columns. They just simply stay out of the business column, and because that's part of what we want. We want non-business. Now, the other event, being the junior, is located in this row. And so we're going to save that for a little bit, and let's turn back into our writing board right here. But now, when I emphasize that concept about grouping the negation with its partner event, the advantage came out here when you're actually applying that to the compound statement with the OR keyword, because it gives a really good convenience when we're separating it out. The OR here is still the separator, and we can separate it out to looking for a separate probability of being not business. And then we're going to add with a separate probability of being the junior. Being a junior in that class. And then the additional rule says we're going to need to subtract out those being outside of the business major, not business, but then at the same time being a junior. All right, so, and that's how useful the highlighting in my table is going to become for us. And so, not business, now we can just simply total up all these column totals with the pink highlights right here. So 18 together with 70, with 7 right here, which gives me 95 over 104. And the other one, the probability separately for junior, the math is going to give me, and actually the row total is going to give me 14, simply just that, out of 104. And like I said again, and you have seen it quite a few times now, that my style here is that in a lot of these, in the middle steps like this, I'm not going to reduce the fraction until at the very end here. And now we are going to subtract and think again that as we already have finished highlighting our columns that meet the events, and now it's going to be extremely beneficial to find this probability. So all we have to do is look back into our table here, and the intersection entry between the purple, the light purple color, and the light pink color. These are the intersection entries that gives the total outcomes for those being not business, outside of the business major, but then being in the junior class. And so there we're looking at minus 13 out of 104. And so now doing the math, our final comes out before reductions is 96 out of 104, which reduces down to 12 out of 13. And that completes our question H. Alright, so last question of this example. So how about question I? We want to find, let's bring in some conditional probability. So I want to find probability of being a junior given that as an engineer student. And so we have seen in our lecture about conditional probability, then in this way, and I also need to make a note that when we apply conditional probability in a contingency table like this, it's always easier to stay with the count there. And based on our counting fundamental that we're looking for junior, we look for junior within the other event being the engineer major. And so staying on that fundamental is going to help us count extremely easily in our contingency table here. And so let's look over to our contingency table. As I said in the lecture and explained in the lecture, then we're going to need to narrow all of our attention to within the engineer first. And so here's the engineer column, which came down to the column total being 70. And so now, once we have narrowed all of our attention into this column, then we're going to start looking for being the junior students. And so the junior students is found right here in this entry. This is indicating the junior student within the engineering. And so in that way, back to my writing board, looking at the column total, we were having 70 engineering students, and within these 70 engineering students, we had 10 of them being the junior class. And so this is indeed and simply our final answer. And it is now just a matter of reducing that fraction into 1 out of 7. And that's how we apply a conditional probability into a contingency table like this.